Okay, I'm Eric Caspole from the AMD Java Runtime team, and I'm here to explain some stuff about our OpenJDK project Sumatra and get into the technical details of the first JDK prototype that we've implemented using the heterogeneous system architecture. Whoops. Okay. So here's the agenda of, I'll just give you some background about OpenJDK, Sumatra project. Some details about GPU workload fundamentals, because programming for GPU is fairly different for CPU, and there are some things you need to take into account to design a workload that's going to work well on the GPU. Then I'll explain in more detail about this heterogeneous system architecture and our AMD APU product line that have certain features that we've taken advantage of, which leads to why we implemented the JDK prototype the way that we did. And then at the end, I have a lot of sort of action item to-do list. Hopefully that can spur some discussion for the workshop that's in the later session, later today. Okay, so yeah, Sumatra is a project intending to enable Java offload to the GPU, hopefully more or less transparently to the application so that it does not require a tremendous amount of customizing by the application developer, and hopefully with no need to write any native code, so that the solution could be as portable as possible between different platforms. We started this project last fall after some discussions with Oracle people, and we've had a really good back and forth between us over the last year. I've been working on this, and most of the guys in my own group, since about last October, I would say. In terms of why would you actually want to do this anyway? The GPUs really have an awful lot of processing power. Just as an example here, you can see this. In 2000, the world's top supercomputer could do 3,200 gigaflops. But now you can go to Fry's and just buy a card that can do 4,700 gigaflops. And the one that I've noted there, is already obsolete. So there's really a lot of power that you can take advantage of if we can just sort of connect the dots. There are some existing solutions already to enable offloading, but they require more or less customization or native code to be able to do it, and it's not perfectly straightforward, and that's why we are hoping to integrate this directly into the JDK. So, right, the two programming paradigms between CPU and GPU are quite different. Obviously the OS is going to run on the CPU, and for any kind of branchy code, doing your I/O, networking, so forth, obviously that's always going to run on the CPU. For the GPU, you want to have a data parallel workload, and the best, the sort of best example of that is for, graphics processing, just image processing, or just, drawing things on the screen very quickly, and especially in the case it's used a lot for games. And one interesting aspect of Sumatra is certainly to decide if the VM will be able to have enough smarts to determine on the fly what part of any workload may or may not be well suited to offload to the GPU. So that's another area that we will eventually get to investigate. So in particular here about what kind of algorithm are you going to be able to offload? GPU SIMDs, now this is a data parallel programming paradigm, and that really means you're doing exactly the same operation on different data all at the same time. You can basically think of it as basically like 1,000 threads all pretty much in lockstep, all doing the same thing at the same time. And each GPU core gets its own unique ID, and the sort of common way to do that is pass in arrays of data into the GPU, and then each core gets its own workout item ID that it can use as an array index to access the array, and then it will get its own unique piece of data that it's doing. So here's kind of a straightforward example with the for loop. In this case, you can see like each iteration of this loop, there's no dependency between any iteration of the loop. And so you could do this loop all in parallel because there's no dependency between any I or any I plus 1 or I minus 1. Or you can rewrite it there as a stream operation. And if you just insert the dot parallel dot for each, you could do all that work in parallel using Stream API, and you would know that you're always going to get the same answer as doing it single-threaded. Another thing to keep in mind is if you can run your loop backwards and still get the same answer, then you're probably on a good path to have something that's parallelizable. So in the case of for discrete GPUs, and when I say discrete, I mean having a card that you've plugged in to your machine. In order to be able to take advantage of the discrete GPU, your workload has to have certain characteristics that need to be taken into account. So as I said, one thing you really want to have your algorithm has to be fairly straight line code. You want all the cores to more or less be in lockstep with not too many divergent branches, because what happens is if you're running straight line code and you come to like an if-else block, all the cores that take the if block will execute, but all the ones that going to do else are basically predicated off. And so if it's like a 50-50 split, your throughput will immediately go to like half. And then so the if block runs, then the else block runs, and then they sort of reconvene and continue. So it's really, you want to keep that in mind when you design your workload, to have as little branchiness or divergent branches in the code as you can get. In terms of taking advantage of a discrete card, you need to keep in mind that you need to copy all the data to the card over the PCI bus. So in order to get a win, you need to have enough compute work happening on the card to offset the cost of copying the data back and forth. And that's what this picture is trying to illustrate. You want to have, your job should be a lot of compute relative to the amount of data you're copying to make sure that you're going to have a win. This heterogeneous system architecture will erase some of these limitations, because with HSA you'll have direct access to main memory from the GPU cores, and I will get into that in the following slides. So here's just another little bit more background about the workload that you want to do. So for here, again, this is just covering it again, right? Here, this workload, this one cannot be run backwards, right? Because your result depends on what happens in the previous iteration. So you can't run this in parallel because you won't get the same answer every time. And here, this one, the same algorithm using Stream API, again, you can't do this in parallel. So here, this one is adding into one like final result answer, and it's racy, right? So this one cannot be done in parallel unless you add synchronization, which would slow down the algorithm quite a lot. In this case, it's refactored to break out computation of partial sums so that this part could be done in parallel, but then in the end it's going to add up the final sum single-threaded. So sometimes you can work around maybe what looks at first sight some limitation in your algorithm. Maybe you can refactor it a little bit to be able to extract some parallelism. So I want to explain a little bit more about the HSA. The intent of HSA is to be able to standardize the CPU-GPU interaction. There's a foundation that's now includes AMD, ARM, Qualcomm, Samsung, and a couple other companies. And they're all interested in being able to do this because this architecture or these capabilities have a lot of diverse use cases, from servers pretty much all the way down to phones, to be able to access main memory directly from the GPU cores. And it's going to allow, as it says there, it's going to have cache coherency between the CPU and GPU, and it has this idea of pointer is a pointer in your algorithm no matter where the code is running. Another aspect of this is having this HSAIL HSA intermediate language, which is going to be, you could think of it in a way as like, well, that's not exactly right, but as a bytecode representation of the algorithm. And then, so that's like a portable, higher level IL that any given runtime that supports this will translate to their native ISA at runtime. And in our implementation, they call it finalizer, because you can never have enough finalizers. Right, so there's a couple of specifications that go along with this. The HSAIL spec has already been released. There's a runtime spec that is not released yet, and it's being reviewed and worked on between all the companies. Because the HSAIL spec has already been released, the HSA Foundation has sponsored development of a simulator that's already available in GitHub to be able to get development going with HSAIL algorithms. And it's, it's an LLVM simulator that can run on any kind of hardware. So AMD has this new product line called Accelerated Processing Unit, which is the one integrated CPU that includes the CPU and GPU on the one socket. And they've had these for about 2 years now, but there's the new one called Berlin, or in some press called Kaveri, will be the first one to be able to support this HSA software stack. And HSA, we think, is going to be a great platform for Java offload because of this pointer as a pointer concept, and there's no copying over a bus. So whatever you can offload to run on the GPU, you don't have to worry about copying, you just have to worry about having the right kind of algorithm. And it really lowers the bar for what algorithms would benefit by offloading. So the picture there is trying to convey the idea that now you just have one unified memory and you don't have to worry about the copying. Again, here's another one that kind of shows it. In the past, you just had the CPU. The first early generations of APU had the CPU and the GPU were on the same socket, but it did not have the right connectivity to allow this uniform memory access, and the GPU memory was still separate from the main memory of the CPUs. But with the full HSA enablement, it's just memory. And so now you can just offload stuff and directly access the same addresses from your CPU algorithm, and it's going to make the offload scenario a lot simpler. Okay, so now I'll get into more details about what we did in our demo JDK. So we took advantage of the stream API because we thought it was a really nice construct and it fits in very well with how we had in our mind the way that the data parallel algorithms should work. So what we did is we take advantage of having the parallel keyword in the stream, because it means, if the developer explicitly put parallel, it means at least he thinks it's thread safe, and we take it then that will be a good candidate to offload. The mechanism that we do it, we can either force offloading immediately by modifications in the JDK code, or we also wrote it as a C2 compiler intrinsic that could kick in later. But it's just done by invocation count, and it's not done by any kind of analysis of the algorithm. But this was nice because it doesn't require any special coding. It's just a regular JDK8 parallel stream Lambda that we can offload. We did this by adding HSAIL support to Graal, and Vasanth is going to cover that in the next session. And a lot of that work is already checked in, so you can check it out now and build the whole system and run it under the simulator that I talked about earlier. So for the first version here, in particular, what we did was we modified the Java util stream for each op to redirect into HSA. And we did this because the for each, I guess I'll call it side effect operation, fits well with this model where you pass in the array that you want to work on, and then it will just operate on each object that's referenced out of the array. And you don't have to, there's no allocation, or synchrony. It just like it's the most simple, straightforward way to do this. And again, because we have the direct access to the Java objects, we just pass in the pointer to the object array, and we can access it directly from the GPU. And of course, we have some, fallback and so forth to keep for correctness. Right, and so like I said, the JDK diffs that we've made are available as a web rev, and the Graal code is already checked in. So anyone can check this out and experiment with it if they like to. Here's a diagram showing how it works more. So here, so this one's going to do in-stream range, so 0, 1024. So it's just going to be a range of 0 to n for each. Here's your iteration variable, which in this case is called GID, and then you have your Lambda body here. So eventually that percolates into stream API code. So we modified this to extract the Lambda function that we send to Graal, get back the HSAIL text. Then we wrote so let's call it a shim layer called Okra to interact with the HSA runtime, because as I said, the HSA spec isn't released yet, but this is a thing that we can release now as a testing workaround so that you can make progress in experimenting with this. So we send this to Okra. Okra deals with the HSA runtime layer, so it finalizes the kernel into the native ISA state and then runs it. And it can run, we have HSA-enabled hardware in-house, or anybody in the public now can use a simulator. Okay? So in the case of the APUs, the generation of APUs that are available now have dozens to hundreds of GPU cores. It's not as many cores as in a full-blown card, but in the future, I'm sure it'll get to be more and more. Each core, the GPU programming model for all the GPU systems that I'm familiar with have this idea of basically work item. So as each core starts up, at the beginning of the algorithm, each core will make a call to get its own work item ID, which is going to be like a contiguous range of 0 to n, depending on the job size. And then they'll use that work item, usually as an index into an array, so that they can find out what's the data that they're supposed to work with. And as I think I said this earlier, but you really kind of think of it as running hundreds of threads, all more or less in complete lockstep, each running one invocation per invocation. In the code we've done here, we've modified the JDK enough to be able to support the in-stream ranges, object arrays, vector, array list, and I'm working on an in-stream reduce sum operation, but that's not done yet. So we added an extra class into Java util stream to help decompose the Lambda pipeline so that we can figure out what's going on and find the source array to be able to send to the GPU. Let's see, what else? Then in the case of when you're using an object array, we pass the reference to the object array as a hidden parameter to the kernel. In the case of an in-stream range, we don't actually have to pass anything because we use the work item ID that the GPU would naturally get as a substitute for the value in the range. So obviously, I mean, we just support the ranges of 0 to n because that's how the GPU works. I'll show a code example of this a little bit later on. And as I said, so in the for each op code, we use some Graal API to extract the Lambda method and then be able to call Graal and get back our HSAIL text. And then once the kernel is finalized, the Okra layer, for the time being, the Okra layer is keeping track of the native kernels so that if you use the same Lambda again in the same program, you don't keep regenerating it. It's just going to immediately dispatch to the kernel. Okay, so we collect the Lambda arguments pretty much the same way as the consumer object does in the Stream API code, and we pass them down to the kernel, basically the same as the regular CPU code works. So that's, I mean, very straightforward, and you'll see that in the code example. The captured arguments work the same way. Because we have pointer as a pointer, the kernel can access the main memory, and so you'll see in HSAIL code, we're accessing objects in a perfectly natural way, the same as it would look for decomiled x86 methods. So it's a very straightforward way to implement the offload, and you don't have to worry about copying or any kind of different addresses or anything like that. There are some limitations. Because the kernel is finalized, we don't have any way to rewrite pointers embedded in the code, and there's no debug info or anything like that. So in order to access like static fields, we pass in some helper pointers that will be able to, that the code has special sequence to be able to go back and access static fields that would be referenced by embedded pointers in x86 code. Right, and I already talked about the Okra.
Do you have to pin objects in memory because they might get moved by the garbage collector?
Yes, we do. We're right. At this point, right, all our code is JNI, and we're using JNI critical, so the GC is blocked. And that's not the way that maybe an ideal solution would work, but also at this point, the kernel examples we have aren't running for an extremely long time, so far we haven't seen that it's a problem, but it's definitely not the way you would really want it for a real final solution. Okay, so here's an in-stream range example. So this one's just doing like calculate baseball batting average, so it's hits divided by at-bats. So here I use this ordinary Stream API construct to create a player array. Then create an in-stream range to my array size, players.length. Again, have my parallel keyword with for each. So now it means it's going to execute the kernel for each value of n and do this algorithm. And players array will be a capture coming into the kernel. And then it just does this division with this one comparison. And here, so I'll go on and show you the code for that. So keep in mind here, right, in the lambda, for the parameters to the actual lambda function are going to be the captured players array and the iteration variable n. Okay, so here in the HSAIL, Vasant is going to go into more about the HSAIL later, but don't worry about this part. I just really look at the top part here. So here's the function, the signature of the function. So it's captured players array, iteration variable. But when we come to the kernel, it's not like we're invoking every GID, every work item or every stream core, let's say, every stream core individually. We're just like launching the kernel. So what we do is we pass in the captured player array, and then we use the work item ID function or the instruction to get the work item for the kernel, that he'll use that as the index into the players array to find out which player to operate on to do the batting average calculation and then store the answer back. And so that's the way that each stream core finds out what data item it's supposed to work on. Okay, so this one is object stream. And so now I just modified this a little bit to make a stream of players instead of an array of players. And so now I can just do this nicer looking s dot for each, and my parallel is here. So now I have a parallel stream of players for each. So my iteration variable player is p, and otherwise it's basically the same exact algorithm. And so now the lambda function, there's no captures, it's just p, right? It's just going to be the player. So each, for regular CPU side code, the lambda would be invoked with the player. Now in the HSAIL, again, don't worry about all this. So here's the signature of the Lambda function taking the player. But as I said in the earlier slide, we pass in the array to the source stream array, which is it's the array that's actually the backing store, or whatever you want to call it, for the player stream. So we extract that out of the player stream, pass in that reference, and then use the work item ID as the index into that array so that this stream core knows which player to do the calculation on. And so, if I have, I was downloading baseball stats from the web to make this example, and so it's like, about 700 players come to bat any baseball season. So, my range, I have a workload of 700 players, and so each one will use the work item ID to get the index into the array for all 700 players, and each stream core just does one player. Okay, so as I said, this is like a demo version. So there's a lot of limitations, but we can run like straightforward code that doesn't do anything too elaborate. Right now, we don't have heap allocation working, although our coworker is working on that right now, trying to come up with something for that. We have to be very simple algorithm, no exception handling yet. As I said, we're doing JNI calls using JNI critical. We're still looking. We're still considering all the other things that need to be implemented, like synchronization in kernels, whether it's synchronization between the stream cores or synchronization between the stream cores and the CPU side. In the case of HSA, where they could all be perfectly naturally accessing all the same memory at the same time. We don't support having lambdas inside of the lambdas we're offloading. And as I said earlier, because the code gets finalized, and I think this is going to be true of any GPU offload platform, there's no way yet to have debug info or OOP maps, and so there's no embedded constants in the code, and that has some ramifications on how you would do a GC, assuming that you could stop a kernel in the middle of executing, and there's no save points in this yet either. So you can't stop a kernel in the middle of executing and do a garbage collection. Well, I mean, even if we were not using JNI critical. So here's my big to-do list, and I'm glad we have all the smartest people here to help us figure out what the future direction we want to do on this. We like doing it by stream API because it seems a very natural way to have to implement the data parallel model in a way that's easy to read and understand and can be just sort of seamlessly done with no special programming. But then become, the devil's in the details. Are we going to allow GC while the kernels are running? That seems very difficult at this point. Not sure how, like if you have embedded pointers in the code, how is that all going to work? Can we allow any kind of runtime call back into the CPU side while the GPU is running? This is like fantastic future idea, but imagine we had so much functionality we needed to load a new class. Could you actually stop the GPU, call back into the JVM, load a class, fix everything up, and continue? It seems difficult and futuristic, but remotely possible, let's say. We don't have anything yet about exception handling, whether it's within the kernel itself, or are we going to be able to do a throw and catch it back on the CPU side? And keep in mind, if we have hundreds of stream cores executing, and they're all more or less in lockstep, maybe you could have 500 stream cores throwing an exception. You come back to the CPU side, what do you do with that?
Wouldn't the exception on the GPU side be like a crash in memory space?
Well, it depends. If it's like a divide by zero, or it's conceivable. If you had a bad pointer dereference, right, that's one thing. But you can implement a lot of Java level throws and things.
The PPM side for all, a crash in the GPU space is basically takes down.
Right, but you could get into an exception throw scenario that's not a GPU crashing event, right? That you would want to percolate back to the CPU side. Yeah, so I mean, again, that's just another kind of thing on the backlog to-do list to how we're going to completely flesh this out. And again, the synchronization, whether you want to have synchronization between the cores running in the kernel, between the CPU and GPU side, which in HSA, which is doable in HSA, but maybe not in the discrete offload thing where you're copying the memory to the card. Okay, so here's a little more. I mean, I think I just said that, right? Our HSA system is fully integrated with the memory access with main memory, but there's also the discrete card world using OpenCL or PTX, and those are very powerful cards, but you have to copy the memory. And that has a different set of benefits or problems than the way that HSA will work. But from the programmer point of view, you might not want to have to, maybe you don't want to have to think about that, but you would still like to be able to get the benefit of offloading. So that's another aspect to this. And then, like, one of the last things is just how are you going to configure this? Imagine if you have a machine that had multiple cards, or you had the APU and some cards. How would you want to configure your system at launch time or at runtime so that you could determine which offload platform you might want to take advantage of if you have more than one, or would you want to be able to use them all at the same time? So that's just another item in the to-do list. So yeah, so that's pretty much what I have. We have this demo JDK that everyone can download and experiment with if they like, using the simulator and the Okra layer. It's a pull from GitHub, and I have the links at the end. HSAIL is the finalized, the 1.0 spec is out now, and our first set of implementation and fixes is already in Graal. And Vasanth and Thomas will talk about that in the next part. So yeah, I think we're right on the verge of being able to do this in a realistic way. There's still a lot of work to do, but I think our early work here makes us very optimistic that we can make something good happen here.